We will now use our non-zero gammas, the ones we have listed here, to write down all the non-zero connection 1 forms. And it's straightforward to see that gamma 1, 2 is going to be minus root over 1 minus kr square over r theta 2. Now this is a perfectly correct expression, but we are going to take an exterior derivative of gamma 1, 2 when we use the Carta equation. And for that, it's easier if we were to write this in the coordinate basis. So we will go back from theta 2, which is r d theta, to the coordinate basis and write this as root over 1 minus kr square with a minus sign, of course, d theta. Now gamma 1, 3 is going to be non-zero 2, and that's going to be the same expression here, minus root over 1 minus kr square by r theta 3. And using the same reasoning as before, I'm going to go back to the coordinate basis and rewrite this as sine theta d phi. And gamma 2, 3, our last one, is going to be minus cotangent theta over r times theta 3. The theta 3 is r sine theta d phi. So using that, you will get minus cosine theta d phi. So now these are your only 3 non-zero gammas. So now our job would be to calculate the independent curly Rij's. And there are also only 3 of them, R12, R23 and R31 or R13. So curly R12 will simply become, according to the formula, d of gamma 1, 2. This is a Carta's second structural equation. Gamma 1 k with gamma k2. This one requires a bit of calculation. Not much, but still. It's going to be kr by root over 1 minus kr square. Right, that's the derivative. dr wedge d theta. And what about this term? Well, here one advantage is, because of the antisymmetry that you have in the gamma indices, 1, 1 or 2, 2 are both 0. So the only possible term would have been gamma 1, 3 with gamma 3, 2. But this is gamma 1, 3 and gamma 3, 2 is the negative of this. Both have d phi's in it. So they vanish. So that's the only term that you get. This entire sum drops out. And now it's easy to see that this is actually given by k theta 1 with theta 2. What about curly R13? Well, might look like you're in for a bigger calculation here, because this one gives you again kr by root over 1 minus kr square sine theta dr wedge d phi minus root over 1 minus kr square cosine theta d theta wedge d phi. But you have to add to this term, which is gamma 1, 2 wedge gamma 2, 3. That's the only non-zero possible term in this sum. Now gamma 1, 2 has a d theta, gamma 2, 3 has a d phi, so that's non-zero. In fact, when you add them together, what you get is plus root over 1 minus kr square. So this term into cosine theta d phi. So this term is exactly the same as this term. They cancel out. So you're left with only this. And this is simply k theta 1 with theta 3. Note that how much simpler these expressions are also coming out to be in the rigid basis. Finally, earlier 2, 3, and there are no prizes for guessing what this is going to be. This will also turn out to be k theta 2 with theta 3, as you can easily verify. So this is our complete calculation of the curvature 2 forms. And by looking at these terms, you can immediately read off that, for example, R1212 is k, R1313 is also k, and so is R23, 23. These are the only independent components of the curvature tensor in this particular basis. Now, what should be pretty clear from this is the following. If you consider Rijkl, the value is going to be k if and only if the first and the third index, that is I and k, match, and the second and the fourth index match. So you have k, delta ik, delta jl. But that's not all. Of course, we know that you also have R1221, which is actually minus k. So you can have another situation where the first and the fourth index match and the second and third match. So that is I and L are equal and J and K are equal. And that comes with a minus sign. So you have delta IL, delta JK. So this summarizes all the components which the Riemann-Christoffel tensor has for this particular metric. The fact that all the non-zero components are either k or minus k, at least for this particular choice of basis, is behind the special significance of this kind of metric. This actually is called a metric of constant curvature. Now, things may not seem like it is this simple in other basis systems. Of course, we have already seen that Rijkl, when you express that in terms of the original holonomic basis, then of course we talked about R upper I lower jkl. The forms were not that simple. But actually, they really are. Notice that this expression that we have here is by necessity dependent on one particular coordinate system or one particular basis, to be more precise. It depends on using the basis with theta 1, theta 2, theta 3 as your covector basis vectors, and the corresponding E1, E2, E3, which would follow from them by using the theta I Ej is delta Ij formula. The reason why this is not really a statement which would work in all coordinate systems or all bases is simply that this is not really a tensorial equation. After all, on this side you have a 0,4 tensor. Or to be more precise, on the left hand side you have the components of a 0,4 tensor. On the right hand side you do not have components of tensorial objects. Delta Ik and delta Jl, which by their very nature are constant quantities, are not really tensorial in that sense, because in any other basis the delta Ik will not stay delta Ik if you were to think of this as a 0,2 tensor. So, what you have is a problem that this equation would work only in one particular basis choice. That actually is very easily remedied. You can change this to an equation which works in all bases simply by noting that in this particular basis, delta ik's are also the same as gik's, the metric tensor components. So if you were to write this, you would actually have an equation which is valid in all bases for the simple reason that it's valid in this particular one, obviously, and when you change to another basis, both sides are going to transform like 0,4 tensors, and therefore you will have an equation which is valid in all frames. That, after all, is the beauty of having tensorial equations. to verify our formula, at least in one other case, let us take a look at the results that we had already derived before. These were the results for the holonomic basis. Remember where we had used the three basis vectors del r, del theta, del phi. These are the basis vector fields whose values at a particular point P would give you the basis vectors. And in addition to this, you also have the covector duals, which are dr, r d theta. Sorry, not r d theta, just d theta and d phi. The metric, of course, when expressed in this basis or the basis given by these things, was the one we started the first part of the lecture with. That is dr cross dr by 1 minus kr square plus r square d theta cross d theta plus r square sine square theta d phi cross d phi. And the components of the metric tensor for this particular example were simply these: 1 over 1 minus kr square, 0, 0, 0, r square, 0, 0, 0, r square sine square theta. So while this was, as in our case with the rigid basis, a diagonal matrix version of the metric, the entries along the diagonal are actually non-constant values. And we did calculate all the Riemann-Christoffel curvature tensor components for this particular basis, and we found the following results. Now what we are going to do is pick a couple of these at random and verify that our expression that we just wrote down actually works for them as well. There is just one small point to clear up before that, however. Note that our formula, that is this one, was actually written down for all lower indices r suffix ijkl, but you have one upper index in these expressions. We were talking about r upper I jkl. So to see what that is going to be, let's start with ri jkl with all lowers once again. That's g I k g j l minus g I l g j k. And here you need to raise one index, the I, which of course has to be raised in all of these. So let's get rid of all these i's here and we are going to raise them. But note one thing: when you raise one of the indices of the metric tensor itself, or metric tensor components, what you are really doing is you are multiplying jk, for example, by gij to end up with this. After all, raising is done by this g with upper indices, the inverse g. But remember, this is the inverse of this, and as a result, what you get here are the components of the identity tensor or identity matrix, delta jk. Now, while I did say a while ago that delta jk, when you saw that as a covariant 0,2 tensor, is not a valid thing, because even if the components of a 0,2 tensor were delta jk in one particular basis, they will not stay delta jk in another basis. However, if you think of this as a mixed tensor, a 1,1 tensor, then the transformation rule is exactly such that if you start with delta jk in one frame, it will stay delta jk in every frame. So, actually what you have here are the deltas, and that actually still keeps it a perfectly good tensorial expression. This side is a bunch of 1,3 tensor components. On this side, you do have 1,3 tensor components which are being subtracted. So the right hand side also gives the components of a 1,3 tensor. So this is a valid tensorial expression. Of course it has to be, because you started with a valid tensorial expression where all the indices were down and you raised one index. That process keeps the tensor nature of the equation unchanged. Now let us just take a look at any one or two examples of this and verify. Let's say R1212 for example. That has to be, according to our formula, K times delta 11, which is of course 1, times G22. Now what is G22? G22 is nothing but the coefficient of d theta square or d theta cross d theta in the metric, and that's R square. So this is KR square. Perfect. Of course, if you had taken the other thing, R1221, then delta IK would have actually been 0 because it would have been delta 12. But delta IL, delta 11, would have actually been non-zero. So you would have minus 1 times G22, which is again R square. So you would end up with minus KR square. Of course, that's just the antisymmetry here. Now what about one more example? Let's check that. R3113 for example. What does that have to be? According to our formula, it has to give you a contribution only from this term, the minus delta ILGJK term, because that's the one which has a delta 33. So get K into minus 1 coming from the delta IL, and GJK here is G11, which is 1 over 1 minus KR square. So you should be quite satisfied that you are getting this correct expression which you had here already. So at least in this particular case, we have verified that our formula, which we sort of arrived at out of the rigid basis calculation, is actually perfectly valid in all, at least in this basis, and it should really be valid in all bases. Before we end this completely, let me just point out one more issue. Here, it was easy to verify that the two results that we have, one for the rigid basis and the other for the coordinate basis, actually are compatible with each other for the simple reason that you could write down the expressions of the Riemann-Christoffel curvature tensor in a nice tensorial form, which automatically guaranteed that if it's valid in one frame, it has to be valid in any other basis. So, strictly speaking, this check that we have done right now is a bit redundant. However, it might so happen that while you're doing a calculation with an unknown metric, you may end up doing it in different bases just because one basis may be more convenient, but you may want your result in another basis for the simple reason that some other result which you want to match it to is expressed in some other basis. So how would you change your basis from one situation to another? How would these results change? One way, of course, would be to write down the Rijkl components in your basis. These are tensorial components of a 1, 3 tensor, and then just use a standard rule for transforming your tensor components, which actually works fine. Let me just illustrate that there is a shorter route here using the curvature 2 forms, and that's simply this. The Rijs actually are also tensorial objects in the sense that they transform like a 1, 1 tensor. So when you carry out a transformation through lambda is a transformation matrix in this case for the vector components. And that automatically comes with a corresponding transformation matrix for the covector components that we are going to also call lambda with a different index spacing. So in this new frame, Rij goes over to R bar ij, which is given by lambda ia, lambda jb, R ab. This should be pretty familiar to people who have already done, say, a bit slightly advanced course in special relativity, for example. The important point here is these are the so-called contravariant transformation equations. That's the way components of a contravariant vector transform. And these actually are coefficients which tell you how components of a covariant vector transform. Now, in our particular example, we have a very simple starting point. The rigid basis, of course, gives you much simpler results. So, let's say, for our case, the rigid basis is our starting basis. Of course, we did it the other way around, but we can always start with the rigid basis and try to recover from that results for the holonomic basis. Without, of course, using the tensorial expression trick that we used a while ago. This particular method is going to work in all situations. So, note that for our original basis, the unbarred basis, what we are using are theta 1, theta 2, theta 3. These are, of course, the covariant basis vector fields, and they transform to the new ones dr, d theta, and d phi. On the other hand, along with theta 1, theta 2, theta 3, you must have E1, E2, E3, the corresponding basis vector fields, which, of course, in the holonomic basis would go over to del del r, del del theta, del del phi. And what are the transformation rules here? That's easy. Remember, we are thinking of going from this basis to this basis, so you should express dr, d theta and d phi in terms of theta 1, theta 2, theta 3. And that's sort of trivial. This is dr is this times theta 1. D theta is 1 by r times theta 2. And d phi is 1 over r sine theta, theta 3. Once again, I hope that there will be no confusion between this angle theta, which is a coordinate, and these covariant basis vector fields that we are using. So this is how you go from these covariant basis vector fields to these holonomic covariant basis vector fields. What about the E1, E2, E3? Now, remember that theta 1, theta 2, theta 3 were actually given by these results, which we have actually just simply inverted to get to those. Remember to keep the suffix positions correct. Theta 3 is r sine theta d phi. E1, E2, E3 are just dual bases to this one. That is, theta 1 acting on E1 should give you 1, theta 1 acting on E2 and E3 should give you 0, and so on. It should be pretty easy to figure out that E1 should be root over 1 minus kr square del del r. E2 should be 1 over r del del theta. E3 should be 1 over r sine theta del del phi. You can easily check that these will definitely give you theta I acting on Ej is delta Ij. And these are the transformation rules we want, except that they are the other way around. These are rules to get E1, E2, E3 from del del r, del del theta, del del phi. What we need are rules to get del del r, del del theta, and del del phi from E1, E2, E3, which is easy to do. These equations will tell us exactly what the lambda coefficients are. The only thing you have to be a bit careful about is the fact that the transformation coefficients for the covariant basis vector fields are actually the same as the transformation coefficients for contravariant components. So the lambda Ij matrix is actually made out of the coefficients you see here and not here. That is a very critical thing to remember. The lambda ij's are given by root over 1 minus kr square, 0, 0, 0, 1 over r, 0, 0, 0, 1 over r sine theta. On the other hand, the covariant vector component transformation coefficients which form this matrix is actually to be read off from the way in which the basis vectors, not the basis covectors, but the basis vectors transform, and that is why this is what you get. Of course, you may remember that these two matrices have to be related to each other. They are actually transpose inverse of each other. In this case, because the matrices are diagonal, they are just simply inverses. The transpose doesn't change anything. Now, with the help of these coefficients, we can immediately write down the Rij's, or rather the R bar ij's in terms of the Rij's. Remember, for us, the curly R's are the curvature two forms in the rigid basis, and the curly R bars are those in the transform basis, that is, in this case, the original holonomic basis. So, let's try to figure out curly R bar 1, 2. This is just an example. You could pick any one of the others and work it out the same way. I'm just going to do one of them. That, by definition, is going to be lambda 1a, lambda b2. Sorry. This one is a contravariant vector component transformation index. This one has to be covariant vector component transform index. So, this is 1a, lambda 2b, and r ab. Now, because the lambdas are both diagonal, it's easy to see that in this sum, which should have 9 terms, only one term survives. That's the lambda 1, 1, lambda 2, 2, because these are the only two non-zero components here. And the r will, of course, have a 1, 2. So, what is lambda 1, 1? You can immediately read it off here. It's root over 1 minus kr square. What is lambda 2, 2? You have to read it off from this. R1, 2 is k theta 1 wedge theta 2. Now, just to compare this with our results, we need to be able to rewrite this in terms of the dr, d theta, d phi basis vectors. And that's easy. Theta 1, remember, is actually dr by rho 1 minus kr square. And theta 2, on the other hand, is r d theta. So once you plug all of this in, you get the r bar 1, 2. The 1, 2th curvature 2 form in the holonomic basis is given simply by kr square dr wedge d theta. It should be very easy to check whether that's correct. Let's go back to our curly R12s. We had actually calculated that. Here it is, kr square dr d theta. I can actually go ahead and show you that all of these come out from this calculation. But I don't really need to show this over and over again. I'm pretty sure you've got the basic idea. So if for some calculation you have managed to figure out the curly Rij's in one basis, maybe the rigid basis, and you want to go over to the holonomic basis, this is the procedure which is going to work in general. I will finish this rather long lecture, so long that I had to break it up into parts, with an exercise for you. The exercise actually has deep physical significance. If you take this particular metric given by minus e to the twice mu dt cross dt plus e to the twice mu dr cross dr plus r square d theta cross d theta plus r square sine square theta d phi cross d phi, and calculated the curvature tensor components for this. Went on to calculate the Ricci tensor components defined by the contraction on these two indices of Rijkl, that is R, K, I, K, J, and equate this to 0, you will be able to get a set of equations. Here mu and nu are only functions of R. And the equations that you will get for mu and nu, solve them and you would have derived the Schwarzschild metric in general relativity for yourself. You can try doing this either using the holonomic basis provided by dt, dr, d theta, d phi. That's of course a covariant basis vector set. Or it's pretty easy to figure out a rigid basis in this case and go ahead and work it out using that. One important point to bear in mind here is that the G components will form a constant diagonal matrix in this case. However, it's not going to be the identity matrix. It will be minus 1, 1, 1, 1 along the diagonal. So while raising or lowering the indices, you have to be a bit careful about the sign involved. Anyway, I'm pretty sure that if you have gone through all the parts of this lecture, working this out should not be too much of a difficult task for you. So, go ahead and derive the Schwarzschild metric for yourself.